Okay, with that, Pillatsch is our postdoc here, is our next speaker talking about the natural gas pipeline sensor project.
Right. Hi, good afternoon, everyone. I'm going to be talking a bit about sensors for natural gas pipelines. And let me start off with why we're actually doing that. I think it's always important to keep in mind that we're maybe not as far removed from reality here in research than people always think. Why this research? The background is actually a tragic accident that probably most of you know about in 2010 in San Bruno, where a large gas pipeline basically blew up. As far as I know, it flattened about 38 houses, as you can see in the picture, an entire neighborhood. There were, I think, 8 casualties. What happened? What caused this accident? It was defective welds on one of the pipelines. So now you have to think about this pipeline being installed in 1956, when they didn't have any technology like X-ray to inspect the welds. So a lot of the welds were just not done properly or to the standards that we would do them nowadays. And in addition to that, with the increased demands on our gas pipeline system in general, utilities companies tend to overpressurize the pipelines to actually get the gas to the homes and to the people. And, well, that led to overpressurization with defective welds, led to a big explosion on old pipelines. Now, if this is frightening, think about it, that it is here in San Francisco. The entire network underneath New York is a lot older than that. So just something to think about, why this research is actually important throughout the entire country. And then from the recent news, just last Friday in the newspapers, essentially, PG&E is still replacing pipelines that are not complying with the federal rules in 4 areas, one of the cities being underneath Livermore. So that's also food for thought. So what kind of sensors are we developing in the course of this project? Basically pressure and flow sensors. And these are MEMS fabricated devices. You see the flow sensor, flow sensor on the left-hand side. Tiny little device, paddle-based, basically air hits the paddle on this side. You got a variable capacitor on the bottom that changes the capacitance of the device, and then you can sense what kind of flow you have in the pipeline. And in addition, we do pressure sensors, and these are all my colleague Dr. Son Nguyen, who's developing these in the clean room, and he's spending hours and hours fabricating these devices and getting them down to the point. So why do we want to know flow and pressure? If we know flow and pressure inside the pipeline, well, we can, of course, detect overpressurizations to avoid accidents like the one in San Bruno. We can also detect leaks in the pipeline, which is becoming a bigger and bigger topic because recent estimates show that methane leaks in the country are a lot higher than initially expected, and methane is a much more potent greenhouse gas than CO2 is. So we definitely want to limit those emissions as well. So next slide is just the ready-made fabricated devices. So you see on the left-hand side, that's the pressure sensor, so really, really small and cheap. So the idea of making these devices in MEMS and making them so cheap is just that you can then widely deploy them and get like an overview of the entire grid, which is absolutely huge. I mean, the gas pipeline grid in the US covers miles and miles, so you can't just place lots and lots of sensors or solutions out there that cost thousands of dollars. You want to make them cheap so that you can actually get a good glimpse of the entire network. So on the right-hand side, that's the flow sensors ready on PCBs to be mounted. And on the bottom side, the left one, the green one, is coated in silicon carbide coating to actually increase the wear resistance. I'm not going to go into the fabrication very deeply. That's my colleague Son who does that mostly. But this is the initial test setup that we used for the flow sensors. So you see this is just a plastic pipe with a fan, the flow sensor being installed here at the tip. And it's an open pipe, so it's at atmospheric pressure. There's a reference anemometer, component analyzer to actually measure the capacitance and the changes in capacitance, and everything is hooked up to a computer to actually collect the data as well. And then with the variable transformer, we can actually vary the fan speed to see what the sensor does. And these are some of the initial results. So the blue line is the predicted behavior based on simulation. And red and yellow triangles are the actual measurement results. So you can see that the correlation is very, very good. We're achieving very good results. But as I said, only in a lab setup that is at atmospheric pressure. So another part of this project was to design a test bed that gets us closer to real conditions. This is just an overview picture, and I'm going to show a lot more of this later on and walk you through a video as well. But this is what we call a racetrack-shaped test bed. It's basically the same as a gas pipeline. It's steel piping, 6-inch inner diameter. This is an initial stage. Not all of the components were installed at that stage yet. But it accommodates for windows, for actually installing the sensors, having reference flow meters, reference pressure meters, connects to air cylinders to actually pressurize the test bed. And of course, it's very nicely done in Berkeley colors as well, which is really important. But yeah, just a couple of general specifications of this test bed. I thought there was one more slide, which seems to have disappeared. Doesn't matter, general specifications. We are testing, actually this is standing downstairs in this building in the basement. On campus, we are testing up to 200 psi in air for safety reasons. But it is certified, it has undergone the X-ray testing, hydro testing, and everything to give the complete certification to actually use this test bed for methane up to 1350 psi. So we can get to very realistic conditions with this test bed once we move it off-site for safety reasons. Trying to remember what was on that slide that went missing, but I think that's generally the outline, the specs of this test bed. And here's a video. Let's see if I can start that and play this. Basically of how a test is performed when we test the flow or pressure sensors inside the test bed. So this is the flange where the MEMS sensors are actually mounted. They are mounted on a long rod that sticks into the middle of the pipe. And in this stage, there's a pressure sensor mounted to the tip. So you see how tiny that actually is. So one pressure sensor mounted to the tip. We have a second pressure sensor mounted on the base of the rod just to measure pressures at different locations, see what the differences are. Now this is basically, Son is exchanging the pressure sensor, taking it off to replace it with a flow sensor. They are based on the same platform, so it's just a matter of unscrewing it, swapping it, doing the electrical connections. But you can see how tiny it is again compared to the size of a human hand. So yeah, this is the flow sensor doing the electrical connections. This is connected to the component analyzer to actually measure the capacitance before putting everything back together, just doing a sanity check if everything is working properly as we expect before closing it up, because it is a little bit of an effort to put all the bolts back in. So basically, we insert the sensor solution into the pipeline. And this is similar how it would be done in the field at valving stations, for example. You just remove a flange, you stick this in, and then you get the data out with wireless communication. This is, we're using air cylinders for pressurizing the test bed. As I said, up to 200 psi here in the building. And this is all like safety cabinets. It's locked, so basically once the pressure is set, you can't do anything else than just turn it on or off on the control dials. Yeah, you can see it here again. It's just pressurizing, closing, and venting for the test bed. This is pressurizing the test bed takes about 10 minutes. So I did a little bit of a cut here to not have you stare at the screen for 10 minutes until the pressure is up to 50 psi in this example. Then we do have a large DC power supply that we connect as well. That actually runs a fan inside the test bed that generates a flow. That's set here to 50 volts. We have a motor in there that can deliver up to 5 kilowatts, so it's pretty large to get, even at high pressures, to get a considerable flow going. These are the controls for the fan speed. And we have a reference flow sensor on there as well. So as we change that dial, we dial it up and down. You should be seeing exactly in this shot the flow in standard cubic feet per minute going up. And this is just, as we change the flow, the capacitance on the flow sensor changes as well. So that's the readout of the LCR meter. That's currently for the test stage. Obviously, this would later be integrated into a package with wireless communication that gives you readout of the actual flow speed inside the pipeline. And I think that's pretty much the end of the video, a little bit of an overview of how the test bed works. Exactly, yeah, we're coming to an end. So this is very current research. That video was actually shot, I think, 2 weeks ago. So now for some of the results. Earlier I showed some results of the flow sensors. So this is for the pressure sensors. Now the left-hand side, that's simulation, how the sensor should behave, basically the change of capacitance with regards to the pressure inside the test bed. On the right-hand side, that's the actual that we measured. So there's two things happening here. What you can see is that the general shape of the curve is fairly similar. It starts off fairly flat, goes up rapidly, and then levels out a little bit again. The one thing that we didn't want to see was that the change from 0 to 200 psi here is only about 100 femtofarad when it was predicted to be 8 picofarad. So that's not very good. That's not what we wanted. On top of that, this is a test, actual experimental data, where the pressure was ramped up from 0 to 200 psi. At this stage, we waited for 20 minutes and then released the pressure. So what you can see here is that in those 20 minutes, the capacitance went down, which should not happen. The pressure inside the test bed is constant throughout this entire time at 200 psi. So this led us to believe that on the first prototypes of the pressure sensors, there's actually the seals around the vacuum pods are leaking. And there is another slide here that disappeared, unfortunately. So essentially, I'm going to go into this in more detail. Probably best go back to the very first slide. So these pressure sensors, they essentially have like 100 small little capsules that all have a vacuum inside. And these capsules need to be sealed very well. And it just seems that these seals are leaking. And so currently, we're working on adjusting the process in the clean room to make sure that these seals are tight. And we are almost there to run a new batch of experiments to make sure that we get the results that the simulation actually predicted. So then in summary, you've seen low-cost flow and pressure sensors for gas pipelines. The reason being, generally deploy them on a large scale to avoid accidents as they happen in San Bruno, and as they are still happening in a smaller form every day or every 2 days in the US, and as they could happen again pretty much everywhere. We also have developed this very nice gas sensor test bed that gets us very close to the real world, I would say, in a very adjustable and expandable way, which is really nice. Even though this project is coming to a close fairly soon, this is definitely a facility that we have for future projects and for future research in the area. Then we did see some leakage issues with the initial pressure sensors, but we have a very good idea of where they are coming from and how to address them. And then the testing of the flow sensors inside the actual testbed is currently in progress. But as you've seen in the initial slides, at least at atmospheric pressure, they actually perform really well and really close to what we expected. Yeah, so that's it for my talk. Thank you.
Any questions for Pitt?
Pitt, I'm sorry I missed the first couple of minutes, so you may have already said this, but can these same pressure sensors work for lower pressures, gas pressures, as you might find in a residential water heater?
So the principle of the pressure sensors is essentially the same. For those applications, I would almost say for lower pressures, you could easily buy sensors that are very cheap. These sensors, the specialty is that they work at very high pressures as well.
I agree that they're very cheap, but having just run into a problem myself recently, they're mostly based on diaphragms, and and if they get out of calibration, you basically have to replace them. So they're not cheap in a sense, and they get out of calibration just by bumping them sometimes.
Oh, okay, that's very interesting. Well, I would have to almost defer that question to my colleague Son. But I would say, yes, they can work for different pressure ratings. I think he actually fabricated different versions of it, some to test in pressure ranges from 0 to 200, and some to test at very much higher pressures. But maybe he can comment a little bit further.
Yeah, so by changing of the thickness of the diaphragm, so we can vary the measure range of the pressure. Yeah, so at the moment now, the device we develop here have about 2 to 3 micron of the polysilicon or the zinc carbide, so many variations. But if we reduce the thickness of the diaphragm, so we can measure the lower range. That easier than to design higher pressure.
Yeah.
Oh yeah. So the natural gas contains a sulfur compound for odor, so I guess you take that into account. That the materials of construction, like you probably can't have copper or cadmium parts in there; they'll corrode. I just wanted to mention that.
So the compounds for the odor, actually, to my knowledge, in the transmission line and distribution lines, they are not added yet. They are only added much later when the gas comes to your house. So if we are talking about transmission lines, I think that would not be an issue. Correct me if I'm wrong, but I'm pretty sure that's the case.
Also, there's the natural gas contains methane, ethane, propane. It's got other impurities in it. So you'll probably want to, when you test it, you may test it for a certain period of time to make sure that you get hydrates, you get condensation in there too. So you may get a little different results than you do with testing in air.
Yeah, absolutely. That's why the test bed is designed for operation in methane. So yeah, we're testing at the moment in air, but definitely the plan is to proceed with testing in methane later on as well. Yeah.
So what heat ranges can these sensors handle? Have you looked at the heat range and how much moisture in content in the gas as well?
So we haven't currently investigated the temperature ranges yet because we only just started the testing with our newly developed test bed. But both of these sensors are capacitive type, and the reason for going with capacitive kind of sensing was that in general capacitive sensors are very stable with temperature. So we expect at least temperature changes as you would see them in a pipe not to be a very big issue. As for the humidity, one thing that we've seen in the very initial tests that we definitely want to investigate is there are certain particles and impurities, be it like dirt or sand or whatever, in the pipe, and we're not quite sure yet as to what degree they would stick on the sensors. And that might be to do, depending how humid it is inside the pipeline, they might stick or adhere to the sensors in a stronger way. So we observed that happening, but we don't have the data yet to say how much of an issue it is going to be. But it's on our radar, definitely.
Okay, thanks very much.
Thank you.